Hello YouTube. Today I'm going to be talking about one of my favorite things in math, and it is the infinite power tower. Now, this can be expressed as x to the 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 x dot 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 going on forever. Now, you would normally assume that this wouldn't converge unless it was between 0 and 1, because if it was anything more than 1, it would go to infinity, right? Well, actually, there's a small range, a little bit bigger than 1, where you can raise it to the power of itself infinite amount of times, and it still converges to whole numbers, or real numbers. And so I'm going to show you the range is actually e to the negative e and e to the 1 over e. And I'm going to show you why that is true for this range. So what I'm going to do is convert it into a Taylor series sum, and then I'm going to use the ratio test to find the radius of convergence. So what we first do is let's make y equal to this. So if we raise x to both sides, so x to the y and then x to, since there's already an infinite amount of x's, if you raise x to this, it wouldn't change it because it's infinite. And since it's infinite, it's the only function that can do that. Because if there was a finite amount, then it would change the function. So if you raise x to the y and you raise this will still be y. So basically, x to the y is equal to this, which is equal to y. So y equals x to y. This is the exact same expression. These are equivalent. This is just a much easier way of expressing it. Now, how do we get this in an actual function? Well, what we have to do first is we have to look at a different function called the Lambert W function. And it is the solution to x equals y e to the y. Now, normally there probably wouldn't be an actual solution to this it doesn't really make any sense of how you would find a solution. So if you don't even need to know that it's the Lambert W. You just assume that there's a function that's the solution of this. Now we take the derivative of this and we'll use it for later. And that derivative is equal to 1 over x plus e to the wx. Alright, so this is w prime. And the inverse of this, I'll call it f of x, is equal to x e to the x. Okay, so if I plugged in natural log of x for it, f natural log of x equals x natural log of x, because natural log of x times e to the natural log of x would be x times natural log of x. And so then, since this is the inverse, if you undo it, the natural log of x is equal to the w of x natural log of x. This is important because it'll help us solve this equation up here and turn it into a actual function that we can use. So these two properties are very important, and it'll help us solve this. So, and put that up here. So I'm going to go back to our equation of x to the y equals y. Take the natural log of both sides. So natural log of y equals y natural log of x, because I brought the y down. And I'm going to divide the y over here. So 1 over y natural log of y equals natural log of x. I'm going to multiply both sides by -1. And when I multiply it right here, I'm actually going to put the -1 into the exponent inside of here, so it'll be y to the -1. So that'll be 1 over y natural log of 1 over y is equal to the negative natural log of x. All right, and if you look, x times the natural log of x, the w of that is the natural log of that, which means if I took the w of both sides, then that means the natural log of 1 over y is equal to the w of negative natural log of x. All right, and so I'm going to put e to the power of both of these. So e to the w of negative natural log of x is equal to 1 over y, and this is actually equal to, since if we look, y e to the y, since y is w of x, so if this is a y, then it would be like, what's the word? What's in here over one of the y's. So what that means is 1 over y is equals to negative natural log of x over the w of negative natural log of x, which means that y is equal to negative w of negative natural log of x over the negative, natural log of x. All right, so now that we have that done, what we are going to do now is we're going to find the Taylor series expansion of the w, and then we can plug in negative natural log of x for x in the w expansion, and then divide it and multiply by -1. So I'm going to circle that to make sure I remember for later. And I'm going to take some derivatives. So I already have one derivative right here. So the w of 0 is 0. That's just a trivial thing. The w of, w prime of 0, is actually 1. W prime of 0 is equal to -2. W prime of 0 is equal to, what is it? It is, 9, I think. Yeah, I believe so. Yeah, it is. So, if you keep going, you'll figure out the pattern is equal to negative n to the power of n minus 1. That's what these are. So, other than, 0, you can't do 0 to the -1. But if you do 1 to the 0 is just, -1 to the 0 is just 1. Here, negative 2 to the power of 1, and then here that would be -3 to the power of 2, which is 9. So that's the pattern right here. And so that means since we have the 0 of the nth derivative, we can turn the w function into a Taylor series of equals 0. I'll start at 1 to infinity of negative n to the n minus 1 times x to the n over n factorial is equal to the w of x. So this is the Taylor series for the w of x centered at 0. And now we're going to plug in, we're going to plug in the values from right here. So here's the w. So the negative w of the negative natural log of x. So negative, and then here's the w of negative n to n minus 1 of negative natural log of x to the n over natural log of x times n factorial All right, now this is where it gets really cool because of how much it simplifies. So you can get rid of that, and then you make that n minus 1. And if you notice, they both have negative 1s here. So you can take the negative 1s to the n minus 1 and actually multiply them together. Oh, wait, my bad. This is actually, I'm just going to do times negative 1 to the n minus, to the n. Sorry about that, because I only divided by the natural log, not by negative natural log. So now you multiply that here, and that makes it minus 1, and you can get rid of that. And then these two, the negative 1 here and here, cancel out. So you're actually left with n equals 1 to infinity of n times natural log of x to the n minus 1 over n factorial. I believe. Yes. Wait. I'm almost certain. Yes. Okay. Just make sure I'm not making any mistakes. So now that we have this, we're going to find out, this is equal to x to the x to the x to the x to the x. So we're going to figure out for what values does this actually converge, and how do you figure out if a sum converges? Well, if you look at this, you do the tests, the infinite series tests. So if you look at this one, you can see that it looks like something you'd want to do the ratio test on. So the ratio test is the limit as n approaches infinity of the absolute value of n plus 1 times to the n times natural log of x to the n over n plus 1 factorial. Yes, and times n factorial over n to the n minus 1 times natural log of x to the n minus 1. And it has to be less than 1 to be convergent. All right, and there's going to be a lot of cancellations here. So first we can cancel n factorial with this factorial. And what else can we cancel? We can cancel natural log of n minus 1, if we get rid of the n. And we can get rid of this n plus 1 if we make this n minus 1. Okay, so I'm going to rewrite that on a new page. So the limit as n approaches infinity, the absolute value of, I'm going to write it a special way, of n plus 1 over n to the n minus 1, because they both have n minus 1 in common, so you can put them under that, times the natural log of x is less than 1. Okay, now this is when it gets kind of cool. My mind was blown the first time this happened. It like freaked me out. All right, so if you look, you can divide the n by n and the 1 by n, so you actually end up with, so I'm going to do the positive one first of the absolute value because there's two answers. So I'm going to do the positive one, and that positive one would be 1 plus 1 over n to the n minus 1 times natural log of x less than 1. Now, does this look familiar with the n minus 1? This is actually e. This is the definition of e with the n minus 1, but since it goes to infinity, it doesn't matter. This is literally the definition of e, which I thought was really cool because I didn't even notice it, and it took me so long to figure that out. So that means e times the natural log of x is less than 1, which means you divide by e, so 1 over e, and then e, so that means 1 over e, so natural log of x less than 1 over e. So that means e to the power of 1 over e is that greater? Yeah, it's greater than x. So we got our first bound. And now we're going to do our second bound back up here. So it would be greater than -1 for the for the other one. So as n approaches infinity of n plus 1 over n minus 1 times natural log of x is greater than -1. And now we are going to, so that's e. So e ln of x is greater than -1. And we're going to raise both sides. We're going to first divide by natural log of x. So e is greater than -1 over natural log of x. And then we're going to raise both sides to e. So e to the e is e to the, oh gosh. E to the e is greater than -1 over natural log of x. All right. So then you multiply and then divide. So then that means natural log of x is greater than -1 over e to the e, which is also e to the negative e. Wait, did I do something wrong? I feel like wait, let me check my notes. Wait a minute. I feel like some. Sorry about this. I'm just checking my notes about something. Okay. Oh, my bad. You don't do that. Sorry. I was going to say. So, back to here. You raise e to that, so it'd be e. Actually, my goodness. That would. I would switch the negative ones to get. Yeah, there. Yeah. What the heck did I do? Oh, okay. You multiply by -1, so you get e natural log of 1 over x is less than 1, and you divide that. So e is less than 1 over natural log of 1 over x, and then raise e to that power. So e to the e is less than 1 over natural log of 1 over x. So that means e the negative e is, oh, I feel like I did something wrong again. How did I get e to the e? I am so sorry that this is happening. Let me look at, I have it somewhere on paper. E was right here. One. Oh, I think I just figured it out. So you have e the natural log of x is e the natural log is greater than -1, and then you raise x. Yeah. I think you raise the, so it'd be e. What in the world is happening? X to the e is greater than 1 over e, and then nope. How did I get? There's a way. I am so sorry. There's something I did wrong somewhere along the line. Divided by negative. I think you just take the. I guess it has to do with how the absolute values on here work, but you actually get e is greater than the natural log of 1 over x after, I think you divide 1 over the natural log of x, negative 1 over the natural log of x, and it, like, I guess it cancels itself out. Wait a minute. So you raise e to both sides, so e to the e is greater than 1 over x. So then x is greater than e to the negative e. I'm sorry that took me so long, but basically e to the negative e and e to the 1 over e are the two bounds where you can actually raise itself to its power an infinite amount of times, so x to the x dx. The square root of 2 is actually in between these two numbers. I think these numbers are like 0.06 something and 1.44 something. I don't know. But the square root of 2 is actually in between it, and it's a really weird property, but the square root of 2 in an infinite power tower is actually just equal to 2. So yeah, thank you guys for watching, and that is how you find the bounds of an infinite power tower for other numbers than 1.